So in this video, we're going to continue with our examination of the Wilcoxon t-test or signed rank test. And just to review the 8 steps once again, the first step is to determine those different scores for each pair. We keep the same order, so we always subtract the first column to the second column, so the first column subtract the second column, and then we determine the number, the new n, for the non-zero different scores. We then assign ranks to those non-zero different scores. Once again, we ignore the sign of each difference, and then we create 2 more columns by separating the ranks, and we use the sign of the different scores. So even though we ignore the sign, whether it's positive or negative, in terms of assigning the ranks, we come back to the positive or negative on the different scores and use that in step 4. And then we just add vertically along the last 2 columns we created, so we compute the sum of the ranks for the positive ranked data, and then once again for the negative ranked data. And from that we determine the Wilcoxon t statistic, which is the smaller of those 2 summed ranks, either the positive or the negative in those latter 2 columns. Whichever one is the smaller value is the one we take. And once again, this is a 2-tailed test. So for the 1-tailed test, as a reminder, to do this we would have to predict whether most of the differences will be positive or negative, not keeping open to the possibility that it could be either one. Which is why the 2-tailed test is often the recommended way to go. We then will use the Wilcoxon table on the next slide to find the critical value for the Wilcoxon t, given the fact that we now have 9 pairs, because recall, one of the pairs we dropped out because there was a 0 difference between the 2 repeated assessments, or the 2 repeated scores, at an alpha level of 0.05, and we compare the obtained t to the critical t, and it is significant if the obtained t is less than the critical t. And here we see the critical values of the Wilcoxon signed ranks test, where we have our 2-tailed test, and unless stated otherwise, we're looking for the critical value at 0.05, and we had 9 pairs of data, so that zeroes in on a critical value of 5. Now, as a reminder, our hypotheses, our null hypothesis, is that the median difference would be 0 versus the alternative that it would be not 0 in terms of those difference scores. So our obtained t is the smaller of the 2 ranks, so we have a value of 3, and our critical value from the table is 5, and so that would lead us to reject the null hypothesis. And so we would state in conclusion, because we're rejecting that null hypothesis, the median difference is not 0, so each sample represents a different distribution of ranks versus the red symbol and the black symbol, and we would conclude that different populations of reaction time scores exist between those 2 levels of our independent variable. So we would then bring this back in context to the research question and state that the reaction to a red stimulus would be faster than the reaction to a black stimulus on a computer screen. So this just gives us a sense of the whether there is a difference in those rankings. Another statistic that can be calculated that can bring some a sense of the magnitude of that effect is to convert the obtained t to a z statistic. And this is a prescribed formula where we would just use n, 9 for our sample size. Remember, we dropped out from 10, dropped out the 1 difference score of 0. We would just substitute 9 for n throughout this prescribed equation, and we would substitute the obtained t that we generated from steps 1 through 6. and our resulting z value is negative 2.31. Once again, n is the number of non-zero differences. And so you see here, typically, if we use a z-statistic on a two-tailed test, the significant z-value at the 0.05 level is 1.96. So we can see that the 2.31 is greater than the 1.96, placing the data into one of the tails, and because this is a negative value, we know it's on the negative side, putting us in that critical region of less than 5% of the entire normal distribution. So the z-statistic is often a helpful one to calculate at the very end when using a Wilcoxon t-test to get a better sense of where those data would sit within the population. So this ends our video on the Wilcoxon t-test.